Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the Module 6 Inquiry Question 2 question. This is the 2020 HSC Physics paper, question 28, 7 marks in total. So let's get into the question and see what we need to do. We have a metal rod that sits on a pair of parallel charge plates. You can see here, our little rod here, 20 centimeters apart, that are connected by a copper wire. The rails are 30 degrees to the horizontal, as you can see here. The apparatus is in a uniform magnetic field of 1 Tesla, which is upwards perpendicular to the table. So our magnetic field is going up in that particular direction. A force is applied parallel to the rails to move the rod at a constant speed along the rails. So it moves it up. Okay. The rod is moved a distance of 30 centimeters in 2.5 seconds. Our first question is, show that the change in magnetic flux. Okay, so change in magnetic flux through the circuit while the rod is moving is approximately 5.2 times 10 to the power -2 Webers. Change in flux is a measurement of the magnetic field density times the area that we're in. That's kind of the idea here. We need to take into account our area vector. If you recall, the area vector is always perpendicular to the surface of the area we're calculating. So that's our area vector here. If I try and draw that out, so imagine you're viewing this on the side, a little side view there, you'll see this kind of structure. You have your rails, so that's your rails. You have the magnetic field pointing up in this direction. You have the area vector that is perpendicular to the face of the area, and you have an angle of 30 here. Okay, so what we're trying to find is the component of this area vector. Okay, so this area vector component, we want to work out how, what quantity of this area vector is to our B field. Now, knowing that this is a right angle triangle, we can also work out, given that B is perpendicular to our surface, this is an angle of 60, right, because it adds up to 90, which means that, assuming all sums of a triangle, this is also 30 degrees here. Okay, so the relative spec between my area vector and the value of B is given as cos 30. That's the ratio we see here between the two. Okay, so that's the angle the area vector is to the surface of the magnetic field. So cos theta, because we're not dealing with a flat plane, our magnetic field strength is 1 Tesla. The area, if we have a look, is 30 centimeters in distance. So 30 centimeters going along this way. And in the question, it says they're separated at 20 centimeters here and 30 centimeters here. Okay, so we're going to try and convert that into the appropriate SI units. So 30 centimeters converted into meters times 20 centimeters, which is also converted into meters. That times cos 30, because that's the lift that we see of the area plane. So it's been lifted 30 degrees. Okay, so I'll plug that into my calculator and we get a flux of, that gives us 0.05196 Webers, which is equivalent to an approximation of 5.2 10 to the minus 2 Webers. Okay, so that solves our first question. Off to the next question. It says, calculate the EMF induced between the ends of the rod while it is moving and state the direction of flow of the current in the circuit. Okay, so let's firstly work out the amount of EMF induced, and then we can look at the direction. So EMF is defined as the change in flux divided by the change of time. So how long, how much flux has changed over a set period of time. So according to our question, the rod has been moved for 2.5 seconds and we have a change in flux using the same value as we got from above, to 5.2 times 10 to the negative 2. So next we need to do is put it into our calculator and then work out the direction of the EMF. So 0.02 V, because EMF we're dealing with here, energy. Okay, next we need to work out the direction. Okay, so going back up into our diagram here. Okay, so I know that the force is driving our circuit up in this direction and the magnetic field is going in this direction here. Okay, so that's the original motion of our force. So what we understand from what Lenz's law states is that the EMF induced is going to be opposing the original motion. So the force of the EMF that I produce should be trying to push the rod back down. So that's kind of the idea there. Okay, so if I use my right hand rule, my fingers are pointing up to represent the direction of the magnetic field. My palm, so if I kind of draw the hand here, my palm is pointing away, or if you want to put it like a two-dimensional shape, it's going to the right here. Have a look at where your thumb is pointing. My right thumb is pointing into the page. So that's the direction of the current. So if I look at that on this thing, so if I'm using this as my reference point, I want to generate an EMF force that pulls it back down. Magnetic field is going up like that, which means the current is going back in, goes like that. So this is the induced EMF. So we get this anti-clockwise direction according to the right hand palm rule. Okay, so we get a net EMF of 0.02, and then we also find that the EMF goes anti-clockwise. Okay, next question. Okay, so the final question states that the experiment is repeated without a magnetic field. Explain why the force required to move the rod is different without the magnetic field. Okay, so let's just put this in dot point. So let's look at the consequence of no magnetic field. I'm just going to go back to the diagram we have here. So without the magnetic field, when I push the rod up, there is going to be no change in magnetic flux. hence there is no production of EMF, and so there's no generated force to oppose the rod moving upwards. Okay, so that's what we're going to write. So consequence, no B field means no change in flux, okay, which means there is no production of EMF. Okay, so what's the consequence of that? No production of EMF means no additional force. So no additional force to oppose the motion of the rod. Okay, now what does that mean in terms of the force itself? So how should we title this? Force moving the rod. Another thing you could also say is this basically obeys Faraday's law. So no magnetic field, so no change in flux, so therefore upholds with what we talked about with Faraday's law as well. You need a change in flux in order to get an EMF forming. So force moving the rod is going to be lower, so force is lower to move rod without magnetic field. Okay, there will still be some force required to push it against gravity, but obviously there won't be the consideration of the induced EMF opposing the motion of our rod. Okay, so some force still required. Okay, so just to recap on what I said with this question, there is no production of EMF, hence there is no additional force induced to oppose the moving rod. As a consequence, the overall force required to push the rod is smaller than, or when we don't have a magnetic field in comparison to if we did. We still need some force to push the rod up because we still need to go against the gravitational force, but that is not accounting for any induced EMF, as we don't have any EMF being induced in this example anymore. Hopefully this explains to you how to go through this question. There's quite a lot of different things to unpack here, including the whole Faraday and Lenz's law stuff. And yeah, thank you for listening. Give a like to support the video, and I'll see you next time.